My name is Jacob Siebel. I did my project on the angle change of variable stator vanes in respect to rotor speed in a jet engine. So to start off, what are the three main components of a jet engine? Well, we have the compressor, the combustor, and the turbine. But for this project, we're only going to be looking at the compressor. So what are the two main components of an axial compressor used in the jet engine? Well, we have the rotors and the stators. If you look at this visual here, we have a set of rotating blades followed by a set of stationary blades. Then another set of rotating blades followed by another set of stationary blades. So if you haven't guessed already, the rotating blades are called the rotor, and the stationary blades are called the stators. So the job of the rotor is to spin, suck in air, and impart velocity on the airstream. So it's taking the air, making it go fast. And the purpose of the stator is to kind of catch the airflow leaving the rotors and turn that velocity energy into pressure energy through diffusion. And at the same time it does that, it kind of guides the airflow to the next set of rotor blades. So it keeps the flow going straight into the rest of the jet engine. So why is it important that our stators are variable, meaning that they can actually change the angle of incidence? So if you look over here, you have a set of rotors and a set of stators. So the faster the rotor goes, the angle of the airflow leaving the rotor is going to change. So if the rotor goes faster, the angle is going to go up like that. And if the stators don't change, if that angle hits the stator at that angle, there's going to be flow separation over that airfoil. And if there's flow separation, if it's not too bad, it'll just lead to inefficiency. But if it gets worse, it'll lead to an actual compressor stall or an aerodynamic stall. So let's say this angle changes that way. We want our stator vanes to actually follow that and change that way. And if the rotor slows down, the angle leaving the rotor will flatten out. So you want our stators to change and match that angle. So if you look at our velocity triangle, that's basically what that's saying. So we have our two vectors here, the axial velocity, which is the air coming into the jet engine, and then our tangential velocity, which is the velocity created by the rotor spinning. So the resultant vector is the airflow leaving the rotor stage. So if the tangential velocity or the RPMs drop, that air would come in here and that angle would kind of flatten out or straighten out. So you can see how those two vectors will change the airflow leaving the rotor. So it's very important that we know what's going on. So we have our equation for the airflow leaving the rotor. So it's the tangent of the airflow leaving the rotor is equal to our tangential velocity divided by our axial velocity. But really our tangential velocity is just rotor speed times blade radius, so we can replace the tangential velocity with W times R. Using some algebra, we move the tan over to make that arc tan WR over V sub A. But really, like I just said in the last slide, we want our stator vane to be equal to the angle of the airflow leaving the rotor, so we can say that those two are equal to each other. So I just replace that, I sub that in over here. So we have our optimal stator angle is equal to arc tan of WR over VA. So we're taking in respect to rotor speed, so I left that as a variable, and I put it in constants for the other two. And our units are feet per second divided by radians per second divided by feet. So the feet will cancel out, the seconds will cancel out, leaving radians. So our answer is going to be radians, which makes sense because we're solving for an angle. So I graphed the function of this. So you can see as RPMs increase down on the x-axis, our y-axis will give us the optimal angle of what our stator should be. So now let's find out what the rate of change of that would be in relation to rotor speed as rotor speed increases or decreases. So we have our equation from the last slide. To get the derivative of that, we'll need to use chain rule on the arctan. So the derivative of the arctan is 1 over 1 plus the inside squared. So I put the inside here, multiplied by the derivative of the inside, which is 0.2 over 500. So I divided this out and multiplied it by the top, simplified the inside, and then I distribute that exponent out, which gives us our final answer, which is our derivative. So plugging that into Desmos, and I also had our answer is in radians to make it easier to read. I had to convert to degrees here. So you can see as rotor speed increases, the rate of change of the stator vane decreases. So when you first start up your engine, you're looking at about 2% of a degree change for every 1 RPM increase. Whereas when you get up to running speed down here, you're only looking at about 1/10 of 1% of a degree per RPM change. So this is useful to know if you're designing the actuators, whether the hardware or the software, to at different RPMs, whether you're taking off or you're at cruising altitude or you're decreasing and coming into land, you'll need to know that derivative to adjust the actuators so that the stator vanes can be lined up so you don't lead to any inefficiencies or even have an aerodynamic stall. So thank you very much for watching.